Alrighty, next set of instruments. We've talked about 3 of the 7. We've talked about the altimeter, the airspeed indicator, and the vertical speed indicator. There's 4 more instruments, flight instruments to go. And the next 3 we're going to talk about are gyroscopic instruments. And first we're going to learn a bit about gyroscopes and what a gyroscope actually is. And then we're going to learn how to read these instruments and kind of what they are. So let's get to it. Let's start with gyroscopic instruments. First thing you should know, typically the gyroscopic instruments in an aircraft include the turn coordinator, the attitude indicator, and the heading indicator. First, let's talk about how gyroscopes work. So on there on the right is a gyroscope, and they spin, and they work off something called rigidity in space. We'll talk more about that in class. But number 3, they have something called gimbals. That's these things spinning around it. And the gimbals move and the wheel stays in place because of rigidity in space. I'm going to not spend a lot of time on this video talking about that, but essentially rigidity in space just means that the faster something spins, the more momentum it has, the harder it is to disturb. So if you can spin something really fast, like the Earth is spinning really fast, or if you can spin a top really fast, it becomes what we call rigid, and therefore it's hard to move. It's hard to disrupt. It can hold its position. Okay, so we're going to talk more about that in class. Gyroscopes are made of spinning wheels. This is how they work. And the faster the wheel spins, the more rigid it gets. This is called rigidity in space. They put the wheel inside of a gimbal, which can spin in all directions. As the gimbals move, the wheel stays in place due to its rigidity in space. Make sure you have those written down before we go on. So there's this concept of gyroscopic precession. And gyroscopic precession is the tilting or turning of a gyroscope because of pressure. The gyroscope responds in the direction of the spinning about 90 degrees from the pressure was applied. This can cause drifting of your flight instruments during flight, so they read erroneously. Now, let me explain this really quickly. We'll talk more about this in class. You got something spinning this direction, okay? So it's spinning on your screen. I think that's going to be maybe counterclockwise. But anyways, it's spinning in one direction. If you apply force to it, okay, and it's spinning in that direction, it won't move that way, okay, as you applied force here. It doesn't move that way. It actually moves in the direction of the turn. So it's going to move this way because it was turning that way. So actually yours would be that backwards. It would go that way. So if you apply the force to the side, it goes 90 degrees to where the force was applied, moves in that direction. If you ever spin a top, just tap it with your finger and you'll notice that it doesn't go the way that you tapped it. It might start that way, but it'll actually go off 90 degrees in the direction of the rotation of the gyroscope. We'll talk more about that in class. That's a tricky concept sometimes for the brain to grab a hold of. So there's a couple different ways that they're powered. Most are powered by some sort of vacuum system within the plane. So let's talk about that. We start with an engine-driven vacuum pump. If this isn't in your notes, I just thought about this. If this isn't in your notes, draw this somewhere in your notes. If there's space for it, I may have put space in your notes. I can't remember for you to draw it out. If not, flip it all the way to the back page and draw it in there because you're going to want to have a picture of this system. It's kind of complex. That's why I kind of broke it into pieces. First, we start with an engine-driven vacuum pump. If it's engine-driven, that means the engine has to be on for it to work. Okay, this doesn't work when you're sitting on the ground with the engine off. Then you have a vacuum relief line. All right. Then these get pulled through these into this pump. Now I want you to notice something. Look at these arrows, how they're being pulled in here. The air's coming from somewhere. It's actually being pulled backwards through the instrument towards the pump. The pump isn't moving air to the instruments. It's pulling air through the instruments so they spin real fast like a water wheel, but they're spinning real fast due to all the air passing through there and going through this relief valve, and that just helps regulate the pressure to the pump. And then there's just an overboard line where it spills the air out. There's your heading indicator, there's your attitude indicator, and those are gyroscopes. And we have some sort of filter that's being pulled through So it's got clean air. We don't want to put dirt and stuff inside of our gimbals and stuff. It'll gum them up. And then also being pulled, air is being pulled through the suction gauge through the same system, so we know how much pressure this engine-driven vacuum pump is actually producing. The suction gauge right there. This is what one looks like if it was up and operating. Right now, this engine must be off. It would be right in this kind of 5 inches of pressure range here. But where's the turn coordinator? Well, turn coordinator in a lot of aircraft is not on the vacuum system. It's still a gyroscope, but it's not a vacuum system one. Look right there. It says DC electric, meaning that this is an electrically driven gyro. And I've actually flown lots of planes where the attitude indicator is also electric. So it just depends on your plane, but they still have gyroscopes inside of them. In this particular case, this one would not be part of the vacuum system. The reason why, just so you know, and we're going to learn about the heading indicator and stuff in a little bit, but it's because that way they're redundant, meaning that they're in different, there's a redundancy. So if one system fails, you can still use instruments from another one. So you like to kind of divide out your instruments into different systems. So if one system fails, you still have other instruments still working. They don't all fail. Alrighty, so here's the inside of the turn coordinator. This is an electrically driven gyro. So this thing's spinning real fast. We got a gimbal here. We have a little airplane attached to that. This just basically shows bank, and we're going to learn more about the turn coordinator here shortly. But it's an electrically driven gyro that is set on gimbals, and so it can kind of shows how your aircraft is turning, what the rate, what the quality of its turn is. Let me just fix one thing here. There we go. All right, let's see what we have next here. So, turn coordinator shows you the quality of your turn. It also shows the rate of your turn, and it's actually 2 gauges in one. It's a slip skid indicator and a rate of turn indicator. So quality of your turn, we're going to talk about what that means if you're slipping or skidding, like is your tail actually following your nose? You're not like drifting or inside or outside of a turn. And it also measures your rate of turn. So let's kind of unpack that just a little bit here. Make sure you have those in your notes. First of all, this is your rate of turn. This is straight and level. But if you put your wing on this, so you're turning left and your wing is touching this line right here, you're doing a 2-minute 360-degree turn, or you're turning 3 degrees per second. So after 60 seconds, you turn 180 degrees. So you could actually time your turns and roll that on headings. This is really handy when you're flying instrument flying. And there you go. How many degrees will I turn in 60 seconds? Well, 60 seconds, and I'm going 3 degrees per second. So 3 times 60 is 180 degrees. And there's some old school ones like this would be your slip skid indicator here. This is kind of a more modern one. And when you have a slipping turn, we'll talk more about this in class, but basically your tail, you don't have enough rudder and it causes it to slip. And the up aileron creates a lower angle attack. So you basically have this kind of weird, kind of funky turn that you're trying to do. Sometimes you do these on purpose, but most of the times you want coordinated turns. So if you're slipping, the ball swings to the inside of the turn. See, we're turning right and the ball's on the inside, okay? As opposed to skidding, right? This is when it goes to the outside of the turn. Then we get the tail skidding to the outside of the turn. So skidding, slipping. Skidding, slipping, okay? So we'll talk more about those in class. Coordinated turn, you have the ball in the middle. Before I move along, how do I fix it? Well, you step on the ball. You use those rudder pedals for the rudder controls. You push on the rudder, and it pushes that ball to the middle. So in this case, I need to step on some right rudder. Step on the ball, use right foot. In this case, I used the right foot. Actually, I'll use right foot, but if it was on the other side, I'd use the left foot. We'll talk about these later. All right, let's talk a little bit about how to read the attitude indicator. The attitude indicator shows the pilot both pitch and roll information. Pitch is nose up and down. Roll is turning left and right. So here's the inside of it. We have a vacuum pressure hitting this kind of water wheel looking thing here. This is the gyroscope, the spinning wheel, and these are the gimbals around it. And as it spins really fast, it erects itself, and the face of the attitude indicator is actually separate. And actually what's funny about it is you're turning and it looks like the gauge is moving, but really the gauge is staying still, and we're actually kind of turning around the gauge in reality. but we'll talk more about that in class. But let's talk about how to read this thing really quickly. This is your miniature airplane, so you set this with this little knob so that it looks level when you're on the ground, if you're assuming you're on level ground. And then you have bank angles. This is like 30 degrees, 60 degrees, 90 degrees, obviously 10, 20, 30 degrees. This little dot's 45 degrees. We have pitch angles, pitch up, pitch down, things like that. So that's how you read those things. When we fly, when we take off in the simulator, we'll pitch up to 10 degrees. That's where we should be on our climb outs. And then we'll go level when we're ready to level. When we're making turns, typically we're making 30-degree banks is what we should be making, 30-degree banks. So, but we won't really use this because we'll be using the G1000 ones a little bit. Heading indicators. Well, heading indicator basically tells you, it's kind of like the compass, but not really. It just shows you directional information. Very similar in building to the attitude indicator, except the wheel is kind of 90 degrees to where the one is for the attitude indicator. But similar, air hits this thing, spins it, creates rigidity in space. And we'll talk a little bit more about why we have to adjust this and everything in class. Because of gyroscopic precession, remember we talked about that, how if you put a force on a gyroscope, it moves it a little bit. You need to reset your heading indicator if it's vacuum driven about every 30 seconds because it's just having all that force pushed on it by the movement of the airplane. And so because of that, we want to make sure that we reset it because it's precessing a little bit each second until finally it's like 30 degrees off, and we're like, oh. And we use the magnetic compass to set it, and we'll talk about the magnetic compass in the next section there. But yeah, that's how we do that. But we basically read this. So right now this aircraft is heading about 260 or 259 on its heading. 240, 270 is west, 300, north is 0, east is 90, south is 180. So this is a look at our G1000 panel from like our simulator here. Very common in training aircraft. Right here, this is the heading indicator. This is the altimeter over here, and this is the vertical speed indicator. This is the airspeed indicator, and this is the attitude indicator. See how it has the lines? 10, 20, 30 degrees, 60 degrees, 45 degrees. 10 degrees nose up, 10 degrees nose down. We'll talk more about that image later. All right, that's the end of this section. The next section will be on the magnetic compass.